Okay, so Lecture 2.3, Circuit Prototyping. When one is building a circuit for a one-time application or for a prototype, it is best to use a temporary construction. Production circuits, on the other hand, are almost invariably constructed as printed circuit boards, or PCBs, like that depicted in Figure 2.7, which is this big green circuit board here. If you've ever broken open a remote control or looked inside of most electronics these days, there are, and even those devices that don't have a lot of electronics on them, still often have a printed circuit board inside them. In your computer, it's called a motherboard. So PCBs, which can be cheaply and reliably mass-produced. So if you're going to produce something for a product and you're going to manufacture many of them, you want to go with a PCB. PCBs have recently become economical for even low-volume projects, with custom orders costing only tens of dollars per board or less, plus the components. So cost scales nicely, so that goes down a lot when you mass produce, but even for relatively small volumes, it's becoming reasonable. I've had a couple of senior design groups build PCBs and order them for their projects, so pretty cool. If a lightweight and reliable prototyped circuit is required, though, constructing the circuit via soldered wires and components is usually best. However, even before this, a more flexible prototype is often required. So once you're to the point where you're like, okay, this is my prototype, it's going to need built in a way that is solidly constructed and can handle a lot of acceleration on it, and it needs to be lightweight, you're probably going to want to just solder wires together and components together. But before that, you're going to want to prototype your board and make sure that your components all work together and that the dynamics of your system are making sense before you take all the time to solder even. So for that, we use breadboards. Breadboards, such as the one shown in Figure 2.8 down here, are plastic and metal boards that have several pinholes for easily building temporary circuits. So these are the pinholes that I'm talking about. Pins and leads can be inserted into the breadboard holes to make connections. So the bus strips or power rails on each side of the boards are marked with blue and red strips. So that's the blue one, and that's the red one on the top, and the blue one and the red one on the bottom. These are all electrically connected, so if I was to draw a line like this, all of those pins are connected to each other, as are all of these. They're not connected with each other, so this one row is connected, and the other row is connected, but the rows aren't connected to each other. Okay, and red is conventionally plus or hot, and blue is conventionally minus or ground, each being connected along a row. The numbered terminal strips run vertically in the center of the board. Numbered columns are connected but split into two halves by the center notch. So, I'll go up to this one. So, these numbered columns are all electrically connected along the column, but disconnected across the spine. So the spine disconnects them. So if you want to connect two wires together, you can place them both in the same column, numbered column, and they'll be connected there, as if you soldered them together, for instance. So that is the basic idea of the PCB. Another thing that's nice is that you can, this spine is set up so that you can easily place a printed, or a chip, a microchip, across it. this has the right geometry for that. So, and the leads can go into these holes. So that's very convenient as well. Great. So chips or integrated circuits, so like a processor, for instance, will be an example, but a very complicated one. There are less complicated integrated circuits that do things like they can be power amplifiers, for instance, and they can do all kinds of things. It can be timers, sensors, all kinds of stuff. An example of a voltage divider circuit is shown in Figure 2.9. Two resistors are shown. So we'll just talk about this figure. So I've got the power rails connected, and I've got two resistors. So one resistor is connected to hot power by this jumper. So there's a little jumper wire, and remember, all this is connected. So this wire connects the power rail to this column 35, and this end of the resistor is in this pin, so in this hole, so it's connected there. The other end is connected to row 40, which is also connected to this other resistor, which jumps over the spine and is connected to everything here, which jumps down to the ground rail, which we've bridged with this jumper there. So we've got ourselves a voltage divider circuit. It's one way to construct it. It doesn't have to be this geometry. I just chose this to demonstrate a few principles. So, yeah. Okay. And those jumpers I mentioned, they look kind of like that. Okay, so they're wires with little pins on the end that are easy to remove and insert into breadboards. So they're very convenient. You don't have to cut different lengths of wire, and if it's a solid core, then you've got stiff wire, and you've got to bend it and fit it into place, which can be fine. But then, yeah, it's more convenient to use a jumper like this. And we've got jumpers and breadboards in the lab, and you'll be using them in this next exercise. Great. Coaxial cables. So connecting instruments, such as function generators and oscilloscopes, to a breadboard circuit requires coaxial cables, which have an inner hot wire surrounded by insulated from insulated from a tubular shield that conducts the ground. So here is an example. So you've got hot core, so this is like our plus, and then an insulator, and then around that is the shield, so that's usually the ground. That's the minus, and then you have a plastic jacket around it. So that's what most cables that you've seen are. So this is true of the all of the TV cable that you've seen. It's coaxial cable, and most of the cables that show up in labs are also coaxial cables. And there are some benefits from that geometry that we're not going to go into, but understanding that it's got two conductors inside of it, it's not just a wire, is key. So you really have to understand that a cable has two conductors in it, one for the plus and one for the minus. Therefore, when an instrument is connected to a circuit via a cable, it is connected in parallel. So if your cable, if we're to look over here, and you've got since there are two conductors, I'm going to just put them side by side, even though we know that geometrically they're coaxial, right? Like this. I'll put them side by side, and we've got a plus and a minus, and if we connect that up to a circuit, say it's to a resistor. That was a very poor attempt at a resistor. There we go. A load maybe, resistor R. And then we connect that up to an instrument. Okay, so maybe that's going to plug into some like source. And meets up some sort of connector there, and we've got ourselves a circuit. Notice this is in parallel, electrically in parallel, and not in series. And so that's an important thing to keep in mind. Great. Bnc connectors. So you've seen the connectors for your coaxial cables for your TV, those barrels with the screw on it, or with the sort of nut-looking connector. In instrumentation, coaxial cables almost universally have Bnc connectors, shown in figure 212. So this is a depiction of a Bnc connector, and this is what's on the front panel. Well, actually, specifically, the female connector is on the front panel of most instruments. So oscilloscopes, function generators, some power supplies, although power supplies often have banana clips like the ones that we have, and many other instruments have Bnc cables. So Bnc connectors. So this is the standard coaxial connector for instrumentation. And one of the things that is important to keep in mind when you're using these is that the male end mates with the female end by there's an inner conductor that goes into this inner hole in the female connector, and the contact is so one of the difficult things about the one that you use for your TV cable is that you don't quite know when you're making good contact. The Bnc connector is designed really well so that these little trying to avoid certain language, these little bumps, we'll call them. These bumps are they mate with grooves in this connector, and you can see part of that here. They mate with these grooves. They slide in, and then when they reach here, you can then twist, and it locks the bump into place. So this is spring-loaded. This connector is spring-loaded this way, so it can extend toward this connector, and then once it locks into place, it can retreat back. So it's sort of nice locking in, and you can feel it when you connect it, and you get a nice connection. And it's important to do that because I've seen a lot of students when they're first using Bnc connectors, they push it in, but they don't turn. Without that turn, you don't get a good connection, and sometimes you don't know what's going on, and it's actually that the Bnc connector is not actually twisted in and connected. Okay, great. So, oh yeah, and then all of this, so this is the inner conductor, the hot is the inner part here, and then all of this external stuff, all of this metal out here and all of this metal out here is all ground. So this is plus, and then this is all minus out here. So you can touch the ground by just touching the external part of the connector. These nominally have 50 ohm impedances, these Bnc connectors. So if you are, this is the standard 50 ohms. There are also some video cables that have 75 ohms. There are some floating around in the lab. They're yellow connectors. Avoid those. Don't use those. They have a different geometry, but it's hard to tell. So yeah. Okay, alligator clips. So in order to connect coaxial cables to breadboards, connectors with alligator clips, shown in figure 213, are often used, and we'll use them. So these are what alligator clips look like. They look like alligators. These each have a single conductor, the black clip typically being used for ground and a red clip for hot. Often they will clip directly to a jumper wire. So you can go from a coaxial cable, the Bnc connector, to alligator clips, to jumper wires onto the breadboard. Okay, so that's the sort of the easy way. There are other ways to do it, but this is in our lab. This is mostly what we have equipped, so this way it works pretty well. Connections with alligator clips are convenient but relatively insecure. So they're spring-loaded and they have those jaws, but it's hard to make sure you have a good connection. They should be used only in very temporary prototypes and never when the circuit is to undergo acceleration. Breadboards in general, they rely on friction to keep the pin into the hole, and if you jolt it, wires will come out sometimes. So just generally not great if you're going to be accelerating it much to use a breadboard for prototyping, but alligator clips are even worse. They very easily lose connection. And sometimes it looks like they're connected and they're not actually connected. So something to keep in mind. Okay, so that's all of the background for the Chapter 2 lab.